Welcome to the Deep Dive, where we take your pile of sources and turn them to crystal clear insights. Today, you've handed us a fascinating sack all about model pruning in deep learning. We're tackling one of the biggest paradoxes in AI, really. These incredible models are getting bigger, smarter. But how do we actually, fit a supercomputer's brain into your smart doorbell?
Yeah, exactly.
How do we get this cutting-edge AI running lightning fast on devices with, almost no power? So we're going on a quest today to solve that very problem, the art and science of trimming the fat from AI, making it lean, mean, and incredibly efficient.
Indeed. And what's fascinating, I think, is how model pruning has evolved. It started off as, well, just a simple compression trick, really, but now it's a critical discipline. It's truly about deploying these high-performance neural networks in places where every bit of compute power and memory is absolutely precious.
Like mobile devices,
Yeah.
embedded systems.
Mobile devices, embedded systems, the very edge of our networks, yeah. And the core challenge, as you see, it's always about reducing complexity, whether that's parameters, memory, or computational cost, without significantly compromising the model's predictive accuracy. That's the balancing act. So this deep dive, it'll guide you from the fundamental concepts right through to the advanced state-of-the-art stuff, touching on those practical trade-offs, and crucially, hardware considerations.
Okay, so get ready, everyone. We're going to discover how we can literally sculpt these massive AI models, find hidden winning tickets within them, and even teach them to be faster on the hardware you actually use. We'll dive into what pruning is, the different ways you can do it, some truly cutting-edge techniques, how hardware plays a surprisingly crucial role, and most importantly, how we can actually apply these ideas. The deep dive, model pruning. Okay, let's start with the absolute fundamentals then. At its heart, what is model pruning and why is it just so indispensable today?
Right. So model pruning is essentially a technique to reduce the size and complexity of those often over-parameterized neural networks we tend to train. Think of it like intelligently removing redundant components, just snipping things out.
Okay.
The main goal is always to minimize that complexity, the number of parameters, the memory footprint, the raw computational effort it takes to run. But, and this is key, without significantly losing accuracy.
Right, that trade-off again.
Exactly. And it's indispensable because, well, without it, you simply couldn't deploy many of these high-performance AI models onto devices with limited resources, like your smartwatch or, a sensor on a factory floor.
That makes total sense, making them practical for the real world.
Hmm.
Okay, so when we talk about removing parts, our sources really emphasize this granularity spectrum, unstructured versus structured pruning. What's the key difference there? And why does it matter so much?
This is a really fundamental distinction, and it pretty much dictates what kind of benefits you'll actually get from pruning. Unstructured pruning is the most fine-grained approach. Imagine that massive web of connections in a neural net. Unstructured lets you snip individual, less important threads, little connections here and there. Typically, you calculate some kind of importance score for each weight. Often, it's just its absolute value, how big it is.
Simple enough.
Yeah, and if it's really small, below some threshold, you just set it to 0, gone. This leaves you with a very sparse network, but the pattern of remaining connections is often quite messy, irregular, scattered all over the place.
So it's incredibly precise, like trimming individual leaves from a bonsai tree, maybe. What's the big advantage of being that precise?
Well, it offers the highest flexibility. You can find and zap truly redundant connections anywhere. This often leads to the maximum compression possible with minimal accuracy loss. Sometimes it even helps the model generalize better, acting like regularization.
Okay, sounds great, but what's the catch? You mentioned a drawback.
Right. The catch is significant. It's what we call the latency gap. Unstructured pruning, even though it makes the model much smaller on disk, often fails to deliver, out-of-the-box speedups during inference. Especially on standard hardware like your CPU or a typical GPU. These processors, they're optimized for dense, neatly organized calculations.
Right, block operations.
Exactly. Those irregular, sparse patterns, they completely disrupt that flow. Leads to inefficient memory access, processor stalls. Basically, it gums up the works. You usually need specialized hardware or custom software libraries to actually translate that sparsity into real speed.
Okay. So a smaller file size doesn't automatically mean a faster model in practice? That's a crucial distinction. So what about the other side of the spectrum? Structured pruning. How does that approach things?
Structured pruning takes a much, bolder approach. Instead of individual connections, it removes entire groups of related weights.
Like whole branches?
Exactly, like chopping off whole branches or even entire sections of the tree. You might remove an entire filter in a convolutional layer, or a whole channel, or maybe even a whole neuron. You calculate importance scores for these larger structures, maybe sum up the L1 norms of weights within a filter, something like that. But when you remove, say, a filter, it has this cascading effect. You have to make corresponding changes in the next layer, too. It requires careful management.
Okay, so it's less precise, definitely coarser, but maybe more hardware friendly. What's the main upside?
You nailed it. The main advantage is it results in a smaller but still dense model architecture.
Dense. Okay.
Which means it runs very efficiently on standard hardware. No special libraries, no tweaks needed. You get direct improvements in inference speed and latency.
But the trade-off?
The trade-off is that it is coarser, less flexible. By removing entire chunks, you risk eliminating components that maybe their total importance score was low, but they might still have been critical for some aspect of accuracy. So you can sometimes see a more significant accuracy drop for the same amount of reduction compared to unstructured.
Okay, so but I'm connecting the dots here.
Mm-hmm.
The choice isn't about which one is universally better, is it? It's more about what you're trying to optimize for.
Exactly right. It's a strategic decision. It hinges entirely on your deployment constraints. If your main goal is minimizing the model's storage footprint, maybe for quick downloads or fitting on tiny memory, unstructured pruning is often, simple and effective.
Makes sense.
But if your goal is reducing inference latency, making it faster for real-time stuff on standard off-the-shelf hardware, then structured pruning is the more direct, practical path to actually getting that speed up.
Got it. Okay, we've covered what to prune individual weights or structures. Now, how about when and how we do the pruning? The sources talk about one-shot versus iterative pruning schedules. What's the difference there, and why does the approach matter?
Right, the schedule is important too. One-shot pruning is, well, pretty much what it sounds like. You remove a large chunk of parameters in one single decisive step, usually after the model's fully trained.
Quick and dirty.
Kind of. It's simple, computationally cheap. But the downside is that this abrupt removal can cause severe, sometimes irrecoverable accuracy loss, especially if you're trying to prune a lot. The network just doesn't get any chance to adapt to such a drastic change. It's like, bang, half your brain is gone.
Ouch. Okay, so it's like tearing off a Band-Aid quickly, but maybe taking some skin with it. What's the alternative? Is there a gentler way?
There is, and it's generally the preferred approach, especially for high sparsity. Iterative pruning. Here, you prune incrementally over multiple cycles.
Step by step.
Exactly. After each small pruning step, say, removing just 5% of connections, you fine-tune the model. You retrain it for a few epochs. This retraining lets the remaining weights adjust, adapt, and recover any accuracy that was lost from that small pruning step.
So the network learns to work around the missing pieces.
Precisely. This gradual process means the network can adapt much better, leading to significantly better performance, especially at very high sparsity ratios, like 90% pruned or more.
Makes sense. The drawback must be time, right?
You got it. The drawback is the higher computational cost. All those repeated fine-tuning cycles take more time and compute power, but often the better end result is worth it.
Okay, a more forgiving process for the model. And how do we actually decide what's unimportant enough to prune in the first place? Is there a common rule of thumb?
Yes. The most common and probably the most intuitive criterion is magnitude-based pruning. The core idea is super simple. Weights with smaller absolute values, or a smaller L1 norm for groups, contribute less to the network's final output. They just don't move the needle much.
So they're disposable.
Pretty much. You can remove them with minimal impact, theoretically. It's a simple method, sometimes called a zeroth order approach, because it doesn't use gradient information, just the weights themselves. But it serves as a really powerful baseline, and it's the foundation for many of the more advanced techniques we're about to discuss.
All right, foundation's covered. General strategy's clear.
Yeah.
Now let's get into the really intriguing stuff, the ideas that kind of make you rethink how AI works. Let's dive into these advanced pruning paradigms, starting with something that sounds almost magical. The lottery ticket hypothesis. What is this winning ticket idea all about?
The lottery ticket hypothesis, or LTH. Yeah, it's a genuinely groundbreaking concept. It really challenges our understanding of why neural networks work the way they do. It basically posits that these large, overparameterized networks we train, they actually contain small subnetworks within them. These are the winning ticket. And the kicker is these subnetworks are initialized in such a lucky way that if you could find them and train them in isolation, starting from their original random configuration, they can match or sometimes even exceed the performance of the original massive dense network they came from.
Whoa, hold on. That's mind-bending. So these winning tickets are there from the very start,
Uh-huh.
before training even properly begins.
That's the hypothesis. It suggests that successful learning isn't just about the training process finding the right weight values,
Uh-huh.
but also about having the luck of the draw with a good initial sub-architecture within that big network.
Hmm.
It's like buying a lottery ticket, and some initializations are just winners.
So what does that tell us about, like, the nature of AI learning?
Yeah.
Is over-parameterization just about making optimization easier? Or is it about increasing the chances of finding one of these lucky tickets?
That's the profound question LTH raises, isn't it? It suggests over-parameterization isn't just for smoothing the optimization path. It's also about increasing the probability of stumbling upon one of these lucky initial sparse structures. It shifts some of the credit for performance away from just the training algorithm and towards the fortunate initial conditions of a subnetwork.
Wow. Okay, so how do you find these tickets? Is it a special algorithm?
The algorithm is actually a specific form of iterative magnitude pruning, but with a crucial, almost weird twist. First, you randomly initialize your dense network, and you save its initial state, let's call it theta 0, your blueprint.
Okay, save the starting point.
Then you train the full dense network until it converges. Standard stuff.
Right.
After that, you prune a percentage of the weights with the lowest magnitude, just like before. This creates a binary mask, ones for weights to keep, zeros for those to prune. Now here's the magic LTH step. Instead of just fine-tuning the remaining weights, you reset their values back to their original saved initializations from that theta 0 blueprint you saved at the start.
You rewind the weights back to their baby values.
Exactly. Weight rewinding, that's the defining step. You bring the survivors back to their original random state. Then you repeat the process. Train this sparser, rewound network, prune more, rewind again, iteratively.
That is genuinely counterintuitive. You throw away all the learning from the dense training, except for the structure.
Pretty much. You keep the structure defined by the surviving weights, but reset their values. Now, there's a practical nuance.
Yep.
For bigger models, like ResNets, research found that rewinding to the weights after maybe just a few initial epochs of training can be more robust than rewinding all the way back to iteration 0. Lets things settle a tiny bit first.
Interesting tweak. But the core idea remains. Winning tickets get their power from their lucky start.
That's the essence of it. Fascinating stuff.
It truly is. Okay, let's shift gears slightly. Movement pruning. This also sounds dynamic, like it's looking beyond just the static weight values.
Movement pruning does indeed offer a more dynamic view. It's what we call a first-order method because it leverages gradient information, the direction the weights want to move. So instead of just relying on a weight's final static size or magnitude, it assesses importance based on its movement, how much it changes during the fine-tuning process.
How does that work? Weights that move a lot are important.
The core intuition is that weights actively moving away from 0 during fine-tuning are probably the most important ones for adapting the model to whatever task you're fine-tuning it for. It actually learns these important scores alongside the weights themselves using gradient info.
So it's less about how big a weight is at the end and more about how much it learned or adapted to get there. Why is that particularly good for, say, transfer learning?
Precisely. Think about transfer learning. You take a model pre-trained on a massive data set like ImageNet, and then you fine-tune it for a new specific task. The initial magnitudes of the weights from that pre-training, they might not reflect what's actually important for your new task at all. Movement pruning excels here because it spots exactly which weights are being significantly modified, which ones are actively learning to solve the new problem.
Ah, that makes sense.
Yeah.
It identifies the active learners.
Yeah. And it's shown great results, outperforming standard magnitude pruning on large language models like BERT in high sparsity situations, precisely because those models are almost always fine-tuned.
Very clever. Okay, one more advanced paradigm, dynamic sparse training, or DST. This sounds like an even bigger shift, potentially ditching the whole prune then train cycle.
That's right. DST is a real paradigm shift. It moves away from that static process. Instead, it's a continuous approach where the network's sparse structure actually evolves during the training process itself.
Evolves during training. How?
Well, DST methods don't just prune unimportant connections as training goes on. They also grow new ones.
Real connections. Seriously.
Yeah. Seriously. It allows the model to actively explore different sparse architectures while it's learning. It's not stuck with the initial random sparse guess.
So it's like constantly redesigning itself on the fly.
Mm-hmm.
Can you give an example?
A really prominent example is the RIGL algorithm. Stands for rigged lottery. RigGL starts with a randomly initialized sparse network. It doesn't even bother training a dense one first. Saves a lot of compute.
Okay, start sparse, then what?
Then, at regular intervals during training, it does two things simultaneously. One, it prunes some existing connections, usually the ones with the smallest weight magnitudes, the usual suspects. Two, and this is the clever part, it grows an equivalent number of new connections. And it tries to be smart about where it grows them.
Where?
It adds new connections in positions that currently have the largest gradient magnitudes. The idea is to add connections where they seem most needed to help reduce the training loss right now.
Wow, that's incredibly resourceful. Pruning the weak, growing towards the potential. What's the main significance of this dynamic approach? Why is it catching on?
Two main things. First, efficiency. By working with a sparse model from the get-go, it avoids the huge computational cost of training a full dense model first. That's a massive time and energy saver. Second, performance. By allowing the sparse mask, the pattern of connections, to change dynamically during training, it can often find better performing subnetworks compared to just training a static sparse architecture from scratch. Static ones can sometimes get stuck in poor local minima. DST keeps exploring.
Very cool. Okay, we've journeyed through the theory, the basic strategies, the advanced paradigms, but now we need to bridge this to reality, specifically speed. You mentioned the latency gap earlier with unstructured pruning. Let's revisit that. Why doesn't just making a model smaller always make it faster, even with all these clever algorithms?
Right. This is such a critical point, and it trips up a lot of people. Unstructured sparsity, where the non-zero weights are just scattered randomly, and creates these really irregular memory access patterns. Now, standard processors, your CPU, your GPU, they are highly optimized for dense matrix operations. They love working on big, contiguous blocks of data all at once. Think assembly line.
Got it.
That random scattering of non-zero elements in an unstructured sparse matrix, it totally breaks that efficient assembly line. It forces the processor to jump all over memory to find the next piece of data. This leads to really inefficient memory access, stalls in the computational pipeline. It just slows everything down unexpectedly.
So even if I heroically prune 90% of the weights using some advanced method, my GPU might still be chugging along just as slowly, or maybe even slower, because it's spending all its time trying to find the remaining 10% scattered everywhere.
Precisely. That's often the case. A highly sparse model might be tiny on disk, great for storage or download, but it could offer zero speedup or even be slower during inference. Unless you have specialized hardware or custom software kernels specifically designed to handle those irregular sparse patterns efficiently. That's the persistent latency gap we keep mentioning.
This definitely sounds like a problem where hardware and software need to shake hands. Are there solutions that actually do that, where the hardware itself is designed to understand sparsity?
Absolutely. And this is where hardware-software co-design becomes absolute crucial. A prime example, and one that's gained a lot of traction, is NVIDIA's 2.4 structured sparsity.
2.4? What does that mean?
It's not random sparsity. It's a specific semi-structured pattern. It dictates that within any small contiguous block of 4 weights, at least 2 of them must be 0.
Ah, okay. So it forces a fixed 50% sparsity, but in a very regular, predictable pattern.
Exactly, and that regularity is the key. This specific 2.4 pattern is directly accelerated by dedicated hardware units called sparse tensor cores, which NVIDIA put into their GPUs starting with the Ampere architecture.
So the chip itself knows how to handle this 2.4 pattern super fast.
That's the idea. This hardware support enables a theoretical performance speedup of up to 2x compared to doing the same math densely.
Nice. And how do you get a model into that format?
The typical recipe is train your dense model as usual, then prune weights to enforce this 2.4 pattern, basically. Find the 2 smallest magnitude weights in each block of 4 and zero them out. And then, critically, you retrain or fine-tune the model for a while to let it recover any accuracy lost due to enforcing that pattern.
That's a really concrete step towards practical speedups. But, 50% sparsity might not always be enough, right, if you need extreme compression. What's the next step beyond 2.4?
That's where things are heading now, towards even more flexible hardware-aware patterns. One area getting attention is generalizing this idea, sometimes called VNM sparsity.
VNM. Sounds complicated.
Conceptually, it's like taking the 2.4 idea but making it more flexible. It allows for achieving much higher sparsity levels, maybe 70%, 80% or more, but still in structured, patterned ways that specialized hardware could potentially understand and accelerate.
So you're getting more fine-grained control over the sparsity level, but keeping it structured enough for hardware. What are the advantages?
Yes, much more granular. The potential advantages are, well, achieving those higher sparsity levels for more compression, which could translate to even greater practical speedups in the real world. It also gives you a finer control knob for balancing that tricky accuracy versus inference speed trade-off. You're not just stuck at 50%. Current research is really digging into this, finding optimal VNM values, developing specialized training techniques like channel permutation, or using things like LoRa during fine-tuning to help models conform to these new patterns.
Okay, so this marks a really fundamental shift, doesn't it? Pruning isn't just an algorithm choice anymore.
Exactly. It becomes a co-design problem. Your pruning algorithm choice is increasingly dictated by what your target hardware can actually accelerate efficiently. The question shifts from how can I make my model smaller to what sparse patterns does my hardware like, and how can I train my model to fit them while keeping accuracy high? It's a whole different ballgame.
A massive shift. Needs deep understanding of both sides, software algorithms and hardware capabilities. Okay, let's get practical. How do we actually do this stuff? What's the developer's toolkit look like, especially if you're in the PyTorch ecosystem?
PyTorch actually has some really nice built-in utilities to get you started under torch.nn.utils.prune. The way it works is pretty clever. It applies pruning as what's called a reparameterization. When you prune a parameter, PyTorch doesn't immediately delete the underlying weight tensor.
No. What is it, though?
Instead, it kind of hides the original weight tensor, renaming it slightly, like weight or rig, and introduces a new thing called a mask. Weight mask. This mask is just a tensor of zeros and ones.
Big ask.
And then it attaches a little piece of code, a forward pre-hook, to the layer. Every time the model runs a forward pass, just before the layer does its calculation, this hook automatically multiplies the original weights by the mask.
So it effectively zeroes out the connections you wanted to prune right before they're used.
Exactly. It achieves the effect of pruning without actually changing the underlying tensor structure immediately, which makes things flexible during training and fine-tuning.
Clever. Can you give a quick conceptual example?
Yeah.
Like, how would you prune 20% of weights in a layer?
Yeah, super simple conceptually. For unstructured pruning, say you want to prune 20% of weights in a linear layer based on their L1 norm magnitude. PyTorch has a function like prune.l1 unstructured. You just point it at the layer, tell it which parameter, and the amount to point to for 20%. Done. And for structured pruning, say removing 2 entire output channels from a conv layer based on their L2 norm, there's a prune.lunstructured function that handles that group-wise removal. PyTorch also offers prune.globalUnstructured, which is quite useful. It looks at weights across multiple layers together and prunes the smallest ones globally, which often gives better results than pruning layer by layer.
Okay, that sounds pretty accessible. But during training, you've got these original weights and masks hanging around. When you're finally done, ready to deploy, you want to make that prominent, right? Get rid of the overhead.
Absolutely. Before you export the model for inference, you call a function like prune.remove. This basically makes the pruning permanent. It directly applies the mask to the weight tensor, actually zeroing out the values, and then it cleans everything up, removes the hooks, the masks, the original tensors. You're left with a leaner, genuinely sparse model ready to go.
Got it. Bake it in. So torch.nn.utils.prune gives you the core building blocks. With those in mind, how would you conceptually implement something more complex, like the lottery ticket hypothesis in PyTorch?
Right. For LTH, you'd use those building blocks. First, you set up your model, optimizer, loss functions, standard stuff. But critically, before any training starts, you need to make a deep copy of the model's initial state predict.
That's the theta zero blueprint.
Exactly. Your pristine starting configuration. You squirrel that away. Then you start the main iterative loop inside the loop. Step A, you train the current model for several epochs. Step B, you calculate and apply a magnitude-based pruning mask using, say, prune.l1 unstructured globally. Step C, the crucial LTH step, rewind the weights. You load that initial state adject you saved right at the beginning. This resets all the surviving weights back to their original random values. But you then immediately have to reapply the cumulative mask you've built up over iterations. This ensures that weights pruned in previous iterations stay pruned even after loading the initial state.
Ah, okay. Load initial values, then immediately remask.
Right. Train, prune, rewind, remask, repeat. That's the cycle that lets you find that winning ticket subnetwork.
That rewind step is so wild but crucial. Okay, what if the built-in PyTorch stuff isn't quite enough? Maybe for really complex structure pruning or specific hardware acceleration? Are there good third-party libraries?
Oh, definitely. The ecosystem is quite rich now. For robust structural pruning, especially when you've got complex dependencies like you prune a conv filter and you need the corresponding batch norm channels and the next conv input channels to be pruned automatically.
Yeah, that sounds like a headache to manage manually.
It really is. For that, a library called torch pruning is excellent. It uses something called a dep graph, dependency graph algorithm, to automatically trace all those connections and prune dependencies correctly. Highly recommended for serious structural pruning.
Nice. Automates the tricky bits. And what about getting those unstructured, sparse models, the ones that create the latency gap, to actually run fast on CPUs?
For that specific problem, you'd look at Neural Magic Deep Sparse. It's not a pruning library itself, but a specialized inference engine. The workflow is usually using your model. You prune your model using their companion library, SparseML, which has various pruning methods, export the prune model to a standard format like ONNX, and then run it using the Deep Sparse engine. They've engineered it to get GPU class performance for sparse models, but running on standard CPUs. It's a big deal for deploying advanced AI more widely without needing expensive GPUs.
GPU speeds on CPUs via Sparsity. That's impressive. Any others worth mentioning, maybe for specific hardware?
Well, if you're targeting Intel hardware specifically, there's the Intel Neural Compressor. It offers a unified API for various model compression techniques, including different flavors of pruning structured NXM, semi-structured NSM, channel-wise optimized for Intel CPUs and GPUs.
Okay, so the choice of library really depends on the specifics. Fundamental experiments, complex structures, CPU deployment, Intel hardware.
Exactly. Torch.nn.utils.prune for fundamentals or building novel methods. Torch pruning for robust structural tasks. Deep sparse for production deployment of unstructured sparsity on CPUs. Tailor your tools to the job.
Great overview of the toolkit. Now, let's try to bring all these threads together. Imagine a real-world capstone project. Applying this to MobileNet V2, what would be the objective and how would we measure success?
Okay, good scenario. MobileNet V2 is a great choice already designed for efficiency on edge devices. The objective could be take a pre-trained MobileNet V2 and prune it using two distinct advanced strategies we've discussed. Let's say Path A, lottery ticket hypothesis for maximum unstructured compression. Path B, structured filter pruning for hardware-friendly latency reduction. We'd benchmark both against the original on a common data set like CFAR10.
And the crucial metrics for success. What would we absolutely need to track?
We'd need a comprehensive scorecard. 5 key things. 1, accuracy, top 1 accuracy on the CFAR10 test set. Can't sacrifice too much performance. 2, model size. File size in megabytes. How much smaller did it get? 3, parameter count. Number of non-zero parameters, the raw sparsity level. 4, FLOPs. Floating point operations, usually in gigaflops. A theoretical measure of computational complexity.
Okay.
And crucially, inference latency, actual measured wall clock time, say milliseconds per image, on a specific target device, maybe just a standard CPU to highlight the differences.
Okay, 5 key metrics. And before you even start pruning, you need that solid baseline, right?
Absolutely non-negotiable. First step. Load the pre-trained MobileNet V2 from Torch Vision. Fine-tune its classifier head on CFAR10 until it performs well. Then meticulously measure all 5 of those metrics for this dense, fine-tuned model. That's your ground truth, your starting point. You need to know where you began to know how far you've come.
Right. Weigh yourself before the diet.
Yeah.
Okay, baseline established. Now, path A, accuracy-focused unstructured pruning using LTH. What's the goal and process?
Path A's goal is maximum compression while preserving accuracy. Would aim for very high sparsity, maybe 80%, 90% parameters removed using the LTH logic. The process would be that iterative loop from section 4.2, train the current model a bit, prune the lowest magnitude weights globally, rewind the surviving weights back to an early training checkpoint, not necessarily iteration 0 for MobileNet, reapply mask, repeat.
Okay, high sparsity via LTH. And path B, hardware-focused structured pruning.
Path B is all about speed on standard hardware. We use structured filter pruning, definitely leverage torch turning here because MobileNet V2 has lots of those dependent layers, conv, the batch norm. We'd apply a L1 norm filter pruning to the convolutional layers. The goal wouldn't be maximum parameter reduction, but a significant drop in theoretical computation, aiming for maybe 50–60% FLOPs reduction, because that should translate better to real latency gains. The process is, again, iterative. Prunes some percentage of filters based on their L1 norm, then fine-tune to recover accuracy. Torch pruning handles the messy dimension changes automatically.
Got it. 2 distinct paths, 2 different goals. And after the main pruning cycles for both path A and a path B, there's still that critical final fine-tuning step, isn't there?
Yes, absolutely essential for both. After you've reached your target sparsity with either LTH or filter pruning, you need a final, often longer fine-tuning phase. This helps the network fully stabilize and recover as much accuracy as possible after the significant structural changes. Typically use a smaller learning rate, train until validation accuracy really stops improving. Don't skip this.
Right, the final polish. Okay, so both models are pruned and fine-tuned. How do you do the final benchmarking and analysis? And crucially, what results would you expect to see when comparing LTH versus filter pruning on those 5 metrics?
For benchmarking, FLOPs and parameters, you can use libraries like ptflops or thop. They analyze the model structure. Latency is trickier, needs care. Set the model to evaluation mode, model.evil. Run a few warm-up inferences first to get caches loaded, etc. If on GPU, use torch.uta.synchronize before and after timing to handle asynchronous execution properly. Then average the inference time over a large number of samples, like the whole test set, for a stable measurement. For an edge device like a Raspberry Pi, even a simple time loop around the inference call averaged over many runs can give you reasonable estimates.
Okay, careful measurement. Now, the expected outcome, the trade-offs.
This is where it gets interesting and really illustrates the core concepts we'd expect. The LTH pruned model, path A. Highest parameter reduction, smallest file size by far, tiny,
Yeah.
but likely minimal actual latency improvement when measured on a standard CPU. It would starkly demonstrate that latency gap of unstructured sparsity. Small, fast here.
Okay, and the filter pruned one.
The filter pruned model, path B, lower parameter reduction than LTH, maybe only 50–60% pruned, but a substantial decrease in FLOPs. And this should directly translate into significant measured inference latency reduction on the CPU. It would showcase the practical speed benefit of structured pruning on standard hardware.
So the punchline from this whole capstone project would be?
The best prune model depends entirely on your deployment constraints. There's no single winner. If storage or download bandwidth is your absolute bottleneck, LTH's tiny size wins. If inference speed on standard hardware is paramount, structured filter pruning is superior, even if the model isn't quite as small. It forces you to define your optimization target clearly.
Fantastic illustration. It really depends on the mission.
Okay, this has been an incredibly thorough deep dive into the world of pruning. Before we wrap up, let's look ahead. What's on the horizon? What's the road ahead for model pruning?
Yeah, the field is definitely not standing still.
Yeah.
One major trend is increased synergy with other model compression techniques. Pruning and quantization, for instance, are natural partners. They attack different things. Pruning reduces the number of parameters,
Right.
while quantization reduces the size or precision of each individual parameter. Think converting 32-bit floats to 8-bit integers or even smaller.
So you multiply the benefits.
Exactly. You get multiplicative gains in compression, fewer parameters, and each one is smaller. This combination can lead to exceptionally tiny and efficient models, really crucial for resource-constrained environments.
That makes sense. Powerful 1-2 punch. What about knowledge distillation? How does that play with pruning? Knowledge distillation is another key synergy. The idea is you use a large, very accurate, but maybe slow teacher model to help train your smaller, pruned student model. The student learns not just from the standard ground truth labels, but it also tries to mimic the output probabilities, the logits of the teacher model.
Why is that helpful?
It provides much richer, softer targets for the student to learn from compared to just hard A1 labels. This often helps the pruned student recover accuracy more effectively after pruning, guiding it away from poor local optimists during that critical fine-tuning stage. It's like having a master tutor guiding the smaller model.
Clever. Okay, synergies are important. What about the big challenges in the emerging frontiers, especially with these absolutely massive models, LLMs, vision transformers taking over?
Yeah, the sheer scale of today's largest models presents a huge challenge for traditional pruning. Iterative pruning, with all those fine-tuning cycles, just becomes computationally infeasible for models with trillions of parameters.
Can't afford to retrain that monster 10 times.
Exactly. So the focus is shifting heavily towards highly efficient one-shot pruning methods. Techniques like sparse GPT or Wanda aim to prune massive models significantly in a single pass, often requiring no retraining at all, which is remarkable.
Wow. Prune without retraining. How?
They use clever criteria, often looking at weight magnitudes combined with input activations, to identify and remove weights with minimal impact, all based on analyzing the pre-trained model. Another related area is sparse fine-tuning, efficiently adapting existing pre-trained models that might already be sparse, or applying techniques that maintain sparsity during fine-tuning with minimal data or compute. It's all about being extremely clever and efficient at scale.
So either prune incredibly efficiently upfront or work with sparsity from the start or during adaptation. Makes sense for huge models.
And tied into that is the broader rise of sparse training,
Yeah.
moving away from the dominant dense to sparse paradigm, train dense, then prune,
Uh-huh.
towards sparse training or dynamic sparse training, like RigGL we discussed, where you train a sparse model right from scratch or let its sparsity evolve.
The efficiency argument again.
Primarily efficiency, yeah. It avoids the massive upfront cost of ever training the dense model. But it comes with its own set of challenges.
Such as?
Things like ensuring stable gradient flow through these very sparse networks during training and preventing phenomenon called layer collapse, where entire layers can effectively become inactive and useless if pruning is too aggressive or not managed well early on. It's an active research area.
A delicate balancing act indeed. Okay, one last point. Making sure everyone is comparing apples to apples when evaluating all these different techniques.
Ah, yes, standardized benchmarking. That's been a significant, almost frustrating challenge in the field. Historically, different papers use different base models, different data sets, slightly different fine-tuning recipes, different ways of measuring FLOPs or latency. It made it really hard to fairly compare if method A was truly better than method B, or if the authors just tuned it better for their specific setup.
Muddy waters.
Exactly. Thankfully, things are improving. Initiatives like Pruning Bench are emerging. They aim to create unified frameworks and leaderboards, especially for structured pruning techniques, with standardized models, datasets, and evaluation protocols.
That sounds crucial for real progress.
It really is. Having consistent, rigorous benchmarking is absolutely vital for the field to measure true progress accurately and ensure results are reproducible. We need that clarity. So if we kind of tie this all together, connect it to the bigger picture, mastering advanced model pruning, it really turns you into a sort of full stack optimization expert, doesn't it? It's not just about snipping out weights anymore. It's about deeply understanding those theoretical trade-offs between size, speed, and accuracy. It's getting fluent in sophisticated algorithms like LTH, or movement pruning, or dynamic methods. And crucially, it's about knowing how the specific capabilities of your target hardware, whether it's a standard GPU or one with specialized units for patterns like 2.4 or maybe future VNM sparsity, how that hardware fundamentally dictates your entire optimization strategy. This isn't just about making models smaller and abstract. It's about making them fit the constraints and fly on the silicon where they actually need to run.
Absolutely. And as you've laid out so clearly, it also demands